for attending this second distinguished seminar of the week. I only need a note to introduce Shinpei Kato. Welcome to CISTER. Shinpei Kato is an associate professor from Tokyo University, and he received his PhD in 2008 from, this is Kato University. And he holds a number of positions, basically most of them in the US, in CMU, and also with Professor Grant in the US as well. I also want to mention that he received in 2006 the annual Young Author Award from IEEE, Computer Science Society in Japan. So basically today he's going to entertain us on how to build an autonomous vehicle from scratch, and this will be something 45 minutes to 1 hour.
Sure.
Thank you.
Okay, thank you very much for introduction. My name is Shinpei Kato. Thanks for coming to the seminar. So I'm going to talk about my project in Japan. So after I joined my previous institute, which is in Nagoya, Japan, close to Toyota. So I have been less present in academic conference for 5 years because of the project. So I'm going to present what I have been doing for in the project, especially about autonomous vehicle. Just brief introduction of myself. So I received a PhD in Japan, and I moved to CMU in the US. And I was kind of fortunate to work with Professor Rajakumar. He is pretty famous in the real-time systems community, and at the same time, he's a founder of autonomous driving project, actually technical lead of the autonomous driving project at CMU now. So he gave me some pointer to an interesting project about a, just the vehicle drives by itself. I didn't really get myself involved in autonomous driving project at CMU, but I always felt that this is maybe interesting project, and when I go back to Japan, I thought that I may want to launch that kind of project. Also, I was working on a multi-core, a GPU, or a supercomputing cloud, and so on. And in 2013, I joined Nagoya University. Nagoya University may not be very worldwide in the sense of computer science, but this is pretty popular university in Japan, so we got a lot of Nobel Prize winners. And this university is located very close to TMC, Toyota. So it was kind of a natural way of thinking that since I joined this university, it is good for us to collaborate with Toyota. And autonomous driving was not very open in Japan at that time, but we anyway started the project. So we have actually multiple vehicles which we can install our software or install our research outcome in order to make it run autonomous. So for example, however, in order to make it research, because I am a computer scientist, for example, putting parallel or distributed computing to the vehicle may be one of the subjects that we can make it involved in the project. But basically, the main objective of the project was to make the vehicle operate by itself. So there was very little set of research, like students are focused on engineering, and they are pretty limited to write papers. But still, we get a lot of nice experiences from such engineering. And I was also fortunate to be synchronized with the opening of University Research Center. So this is academia industry collaboration research center, where a lot of companies are joining. There are examples of such companies. So for example, Panasonic or Denso, TMC, they are very good partners for us because they provide engineers or they provide industrial needs or societal needs sometimes, so that we don't get lost in academia about clear exit of the research project. Well, and now I actually moved to another university in Tokyo, but I still actually have my affiliation in previous institute because the project is still running. So officially I belong to two universities, one is Tokyo and the other is Nagoya. Okay, let me finish my introduction. So we have multiple vehicles and we actually allowed to test autonomous vehicle on a public road. So this is one of the examples. There are no, say, extras, no support cars. It's just on a public road. And we don't know other cars. They just drive and they wouldn't believe that this is autonomous vehicle. They really don't know. But we actually test and drive. So this is made possible by...
Are you driving on the bicycle lane?
This is bus lane, actually.
As a bus, okay.
But that is important because we don't want to be more aggressive in the initial stage, right? So we use bus lane, but it's not dedicated to bus. Any other cars can use that lane, but it's prioritized for public bus.
Okay.
But it's less traffic, so it's more safety. That was our opinion. So, but this is made possible by contacting police. This is very important to talk to police many times to set up the condition and how we guarantee the safety and so on. But eventually we are allowed to test drive. And so we are not car makers, so we don't really not interested in a car itself, but this is one of the examples of the set of sensors. For example, the one you see on top of the vehicle is a LiDAR, it's a laser sensor. And we also have a camera on the front window. That's it. We don't have GPS, we don't have other sensors. We only use two sensors. And this is a demonstration of the scenario where we only have two sensors, but we can still do this. This is TV reporter, so it's pretty complete now. So guests can ride on the vehicle for experiencing a demonstration. And we are driving at almost 60 kilometers per hour, which is 40 miles per hour. So which is pretty high speed. We can sometimes bypass the vehicles driving on the next lane. So sometimes we have to be very careful in case that the vehicle is out of order, then the car may be crashed. So we also have to be trained about how to operate the experiments. So we have to train in case that the vehicle behaves in the wrong way, then you take over the vehicle so that override the way. And now we opened up the project so everybody can use the same software, same vehicle, same sensors. So this is one example in a different place in Japan. They bought the system from us and they did the same experiments without our, well, we do support remotely, but they actually built this system by themselves. So now it's packaged platform. Its platform is pretty important because if you don't have a platform, you cannot recreate or replay the same idea. So I believe that we can contribute to the industry in the sense that we provide a platform so that everybody else can do the same thing as what we are doing. And this is another case. It's not on public road. It's off-road, but the same system, same sensors, camera, and this is in collaboration with Yamaha motor company. You may not know this company, but it's pretty worldwide in the motorcycle market. They have very good share. So now, since we have a platform, we can transform our technology to a different vehicle and so on. So I'm going to explain. So before I'm going to explain, well, of course, as you may know, a lot of car makers are now getting into more market with autonomous driving technologies, but we are very different from them because they are more focused on production. So they don't want to put sensors on top of the roof because it looks ugly. They want to embed sensors in the car because they are looking for the market production. But we are very different because we are looking at 2030, for example. It's fully autonomous. We are not focused on the semi-autonomous. We are not focused on highway. We look for fully autonomous in a citywide area, like Google. Maybe Google is the most cutting-edge company in this domain since they have already tested a few million miles on the public road. So they are very pretty way ahead of our project, but we are trying to catch up with such a company. And so today I'm going to briefly explain how to build an autonomous vehicle from scratch, assuming that we don't have anything yet, but how we can start. So the first thing is that you have to hack the car because the car company doesn't give you a car because it's unreliable. Industry sometimes believes that because university is more open, sometimes the technology or intellectual property may be disclosed, so they are not giving us a whole set of the system, so sometimes we need a hack. But recently, I know a few companies who can help us to hack the car. Hacking means that they modify the car networks to be able to be connected to another computer, so that if you send some commands from the computer, the car actually moves. Car moves means steering, accel, and brake. By, for example, directly sending a signal to ECUs. So you need to analyze what voltage or what range of current are needed to operate the vehicle by wire. But recent, for example, hybrid car, which already has a electronics inside the vehicle. So if you know the protocols or the specification of the wires, then basically you can hack a vehicle. So we are putting, so control box means a kind of PC. So, and the PC is connected to the ECUs directly, and we send the signals to the ECU, then car moves. So after hacking, maybe you can do this, just moving steering from remote. Or you can also record a log of steering angle and accel and brake strokes and just exactly replaying the steering and accel and brake, so that there is no intelligence inside this system yet, but still at least you can move the vehicle by itself. And this tiny modification or hacking still attracts people because we can replay the vehicle driving by itself. This doesn't recognize location. This doesn't recognize objects. This doesn't recognize anything. It's just replaying the vehicle, replaying the path of the vehicle that we drove previously. But still, it attracted the people. Now, since you want to put intelligence in a car, you need to put computers and sensors. There are actually many sensors. Perhaps laser sensors are getting more popular because it can recognize the distance, range information very precisely, but still cameras, GPS, and then radars, they are also popular. So laser sensor, because it's very expensive yet, so maybe automotive or industrial makers, they don't really want to use them because of the price, but in the future, it has a good potential to be deployed in a real system. Now, we have a vehicle, we have computers in it, and we have sensors attached to the vehicle, but we can't do autonomous driving yet because you don't have a system or software or data yet. For highway driving, you don't really need anything else. Maybe you can just need to detect the lanes and control the vehicle to drive inside or between the lanes. That's it. But in a city, since sometimes you don't have lanes, so you really need to understand where you are driving in the city, so that, for example, to understand how close crosswalk or zebra zone is approaching, and so on, or traffic lights. So in order to do so, recently 3D map is getting very popular item to support autonomous driving in the city. And 3D map is it's a collection of 3D points, X, Y, Z, plus colors. This looks like pictures or movies, but it's not. This is a data, three-dimensional data. And there are more than 1 billion points on to represent how the real world looks like. So if we have 3D information about the real world, at least you know how the real world, the shape of the real world looks like around yourself. Plus, shape is a good information for autonomous driving, but it's not enough because we need to embed more information to the shape. For example, which part of the shape are crossroad, or which part are traffic lights, and how lanes are connected. And of course, what are the buildings along the road. And basically, since road is a network, so we have to understand what path could be taken by a vehicle, because you don't want to enter the opposite lane, right? So you have to understand which lanes are available for a driving vehicle. Such a shape information, it's a collection of 3D points, plus road information embedded in data, are often called high definition 3D map. So 3D map means not only the shape of the real world, but also includes the information about road or the real world. So now assume that we have 3D map in a car, and you have laser sensor on top of your vehicle. Well, it doesn't have to be on top of the vehicle, but the top of the vehicle is a good place for the sensor because you can see all around the vehicle, 360 degrees. And laser sensor gets such information. It's a distance information from yourself. And you know something is exists in what range from yourself. You don't know if it's a tree, you don't know if it's a building. Well, if you see it, it's apparently it's a tree or a road. But in order to let the computer understand what it is, it's a very difficult problem. So let's forget it right now. But at least the computer knows something is there. Now, since we have 3D map, the shape of the real world around yourself, and you also have the sensor information around yourself. So if you match 3D map and the LiDAR, laser sensors information, then you exactly know where you are on the 3D map, because they are both the shape information. If the map is correct, then there must be some place which matches the shape of the laser data, because we are in the same place. So we do this processing in real time. When laser sensor data is coming to the system, we try to search on the map where we are. And this process is done in almost 10 Hz because it's a limit of sensor sampling period. But 10 Hz is pretty enough for prototyping, because every 100 milliseconds you know where you are. And this video shows grayscale data represent a 3D map. And those with a lot of circles highlighted by green colors, they represent the data from sensors in real time. So they actually match, for instance, the building. Building is a good landmark because you can use the shape of the building to, say, localize, to compute the angle and the position of your place relative to that landmark. But anyway, so since 3D map, why I forgot to mention, this is a collection of points, 3D map. Each point has a GPS information already. So if you know where you are on this map very precisely, which means that you know where you are on the Earth in this world, it's centimeters order, which is 10 times more precise than high accuracy GPS. That's why we don't use GPS. GPS sometimes, if you go, say, between the buildings, then if you lose satellites, then the positioning may be 1 meter or 10 meters. There's some error, but because we use distance information from the surroundings, we can always keep the positioning in centimeters order. And sensors is also good in the sense that it doesn't get affected by sunlight. It can just work in daytime or midnight and so on. So this is 11 o'clock. Doesn't. Yeah, sorry, I lose. But still, actually, the advantage of the sensor is that it works almost in any time.
Excuse me.
Sure.
So, what is the source of your 3D maps? Is it something that you just got?
It's also a laser sensor. I can show you how we can build 3D map, but it's basically you drive the place once before you test the drive and collect the data.
So, and what is the amount of memory you need to have to save all that information?
A few gigabytes of memory is enough because we download from the cloud. So we put the map in the cloud data center and download it every time you need. And download needs only 1 second for, say, 20, 30 megabytes of data. But 20, 30 megabytes of data can cover, say, 300 meters along your cell. So if you drive in 40 miles per hour, you can only proceed 20 meters in a second. So if you have 300 meters already, so taking 1 second to download, for example, the next area of 3D map may be very reasonable. But I have not yet tested in how it is timeliness. It's just and recently the sensor price is getting down. The cost of the sensor is going down. So like the cheapest one that I have with my project is $8,000. Still expensive, but the one we showed you, it's $150K. It's very expensive usually. So we are now downsizing the sensor, and also the price of the sensor is getting up.
Does it matter if you generate the 3D map with one laser lidar and then use it with another one?
Yes, doesn't matter.
Doesn't matter.
Basically, it's a different car. We have a special vehicle to measure the 3D map, and autonomous vehicles are very different. So we can share the same map with 1,000, million, or billion cars for the same map. We don't have to use the same sensor. So, and we also have a navigation application on the smartphone, which is connected. So if you touch where you want to go, then it can navigate you to the destination. But selecting lane is it's a different problem. So if you know that you only take left lane, then it's easy. But sometimes you have to change the lane to take. In Japan, for a right turn, you have to change the lane. And in Europe, sometimes if you take a left turn, you have to change the lane. So that path selection is another problem that we have to resolve. And for the 3D map, basically the concept is very easy. So assuming that the first LiDAR data, you believe it is a map, and you know the place. So adding the sensor data and localizing the self again and adding the sensor data, since the position is very precise and you know the angle. So if you keep adding sensor data, then you can build the map automatically. So by driving for maybe for 1 minute, then if it's a small parking lot, you can just build a 3D map just for 1 minute. And you upload it to the data center, and now you can share this map with other vehicles. So this is useful because sometimes the buildings are gone, sometimes a parking lot is gone, or sometimes new buildings showing up. So you can ask maybe other vehicles to drive there and collect the new updated information to the data center and just integrate with the previous or the existing map. For instance, this time, if you see a new parking space is built, then you just go there and build a 3D map and connect it to the original map so that you can always keep the map updated. And this is what I mentioned. So since the vehicle doesn't have huge storage, so we only have a 300 meters map in car. But because we have navigation, so you know where you're going to. So when you need to the 3D map ahead of yourself, then you can just download from the data center, and you discard the map which you don't need it anymore, so that you always keep the size of the map almost constant, which is about 20 to 30 megabytes. Definitely it's less than 100 megabytes. So 20, 30 megabytes still big for today's vehicle, but I believe in 10 years ahead, it's nothing. So now we have a map and we know where you are driving. Now, for instance, you can track other vehicles. Now it's shifting to object detection. So object detection has many algorithms. One can be done by just laser sensor, or the most popular approach is image processing. So this demonstration is made only by using laser sensor. Since laser sensor can detect this green highlighted objects are those acquired by laser sensors. If you train your system, then you can assume that maybe on the road, this size of the object could be a car. And once you know he's a car, now you can keep tracking. And the result of tracking is shown on the left display. So we are tracking the vehicle in front of yourself, and he was driving from all the way. So it's very important, because if you can track the vehicle, then you know maybe this vehicle is how this vehicle is moving in 3 seconds, for example. So you can forecast, you can know what could happen in a few seconds. If you don't know what could happen in a few seconds, then you cannot make autonomous vehicle, because when you are driving, you may not be aware, but you are predicting what would happen in 3 seconds. That's why you can drive safely. So we have to make the computer do the same thing in order to realize autonomous driving. So now, until here, we can do without cameras. But cameras are anyway necessary, because laser sensor doesn't know the color. So if we want to see, or if we want to recognize the traffic lights, then eventually you need a camera. Now, traffic light recognition is one of the most difficult problems for autonomous driving, because it's very small. You have to find out what is a traffic light from the picture, and you have to recognize the color. But we can use 3D map information.
How
Sure.
do you distinguish between that this thing is living or non-living, how you distinguish between that? Because if you have to track something, you have to distinguish that this thing is living or non-living.
But what's living?
I mean, for example, if a person is walking around, so if you track that person, I mean, what is the difference? How you have made a difference between these two things?
Sorry, I didn't get it. So,
For example, if a person is like walking on the road
Mhm.
and it is in front of you, and you have said that you have tracked that system.
Mhm.
So how you distinguish that it is living or non-living? And for example, this is a car. How you distinguish between
Oh,
the
I see.
living and the non-living?
Eventually, you need a camera
So
to see who it is, what it is. But the previous demonstration assumes that it's a car. If you know it's a car, then you can track. That's the demonstration.
so you have made some database for that?
Yes, database. It's a machine learning or deep learning. You already have your model to recognize to understand what it is from the shape. From, say, since it's deep learning, we don't know what actually the future, but we have a future database to track the moving objects. So back to traffic recognition. So you know exactly where you are, and you have a 3D map. Basically, since 3D map includes the location of traffic lights, so we exactly know where traffic lights are. So all what you need to do is to see a color, because you know perhaps on the picture. So now it says undefined, because the system cannot see the traffic lights color, but he knows traffic lights must be there. So because of the truck in front of yourself, the system doesn't recognize the color, but at least he doesn't misrecognize this is a red traffic light. Sometimes if you don't have a traffic light information, then by doing image recognition, sometimes brake lamps look like a red light, so it makes the vehicle misunderstand the situation. But since we know where exactly the traffic lights are, so we can just see that position. So now by doing this, we have a small size of picture, but still we can understand the color or the status of the traffic lights, maybe 100 meters ahead of yourself. So now eventually you need a camera to recognize the traffic lights. So why don't you use the camera for object detections as well? Since I'm not an expert in object, say, image recognition, but if you download some open source software, you can just do this. You need to train data sometime, but it doesn't take a few weeks to make this demonstration, even though you don't know anything about the image processing. So open source is very nice. Now at least we can recognize a car and a passenger. So, but I realized that when I downloaded OpenCV, it was very slow. It takes almost 2 seconds to recognize one person on a VGA size of the image. So I used GPU, which is my favorite. So GPU is pretty fast. It can accelerate the processing time by 10 times. If processing is 10 times faster, then you can make this difference. So for the CPU, because it takes almost 2 seconds, it can still detect the person, but because 2 seconds already passed, so the passengers are not there. But if it's 10 times faster than the CPU, so it can only take 200 milliseconds or 100 milliseconds sometimes. So that it can almost keep tracking in, I wouldn't say it's real time, but it's more faster way. But this domain is very complex, since image processing community is very huge. I realized that the people are now using, say, deep learning, or tracking is to predict. It doesn't really detect object every frame, but it can predict from the previous frame information. Fortunately, again, some algorithms already in open source software. So I found out some useful ones. And RCNN is one of the most popular algorithms for deep learning. And if you implement it and test it, then it gives you this kind of quality. But because deep learning is actually useful for those detection which you don't really know the future of the object. Because if you know the future of the object, then you can just apply pattern recognition. So for car or person, because we know the future, deep learning may not really give you huge advantage. You can just still use a pattern recognition. But in order to catch up with the state of the art of the domain, we still work on deep learning. And tracking is it's a kind of prediction. Like Kalman filter is the most maybe entry point of the tracking. So to predict the status of the next frame. But we use a Kanade tracker, which is developed by Professor Kanade at CMU. It's a very famous tracking filter algorithm. So in order to improve the quality of detection, accuracy of detection, you need data. Because you have to do training, machine learning or deep learning. So deep learning, machine learning, they need data. So for instance, we are collecting data. So the reason why Google is very good at autonomous driving is that they have huge amount of data already. So, but we are also collecting in a project that the left side is a LiDAR, laser sensor data, and the center depicts the image data. And if you want to make a model of driving, then you have to also train how the good drivers are behaving. This is brake and also steering axle information. So if you train all of them, then if you see a similar scenario, then you can tell how or what angle and what amount of stroking is required to adjust that situation. That's a kind of deep learning or machine learning. You know, a lot of researchers and engineers in an autonomous driving project, they are working on this kind of thing now. But since I am not algorithm person, so I don't really get into that much, but this is what we are collecting, so I can just give the data set to the scientists to feed me back more accurate model of driving. So this is another thing. So if you have laser sensor on top of your vehicle and camera on the front window, you can make a fusion of two different sensors. So now, because the camera doesn't have distance information, it's just a 2D information. Laser sensor doesn't have RGB information, so it only has a distance information. But say if you know the location relationship between laser sensor and the camera, so you can actually make a fusion, make two different sensors on the same coordinate, same plane, so that say now you can also approximate the distance information into the same size of the image, and putting it together, now it has kind of RGB plus distance information. So you know, say the color information in order to recognize if it's a vehicle or not. Plus, since you have a distance information, when you detect the vehicle, you know exactly how far away from yourself.
So,
Sure.
red means that you're very close to the object. Can you do this before previous slide?
Mm-hmm.
Red means that you're very close.
Oh yes, sorry, yes.
And
Red means close and blue means far.
so why you have that blue on the round image?
Yeah.
Yes, kind of.
There are errors.
Alright.
Because I'm not a scientist. Well, I'm a scientist, computer scientist, but I am not very good at fixing them. So we can just ask other researchers to fix them. So now putting the image processing and laser sensor, laser sensing. So now you know it is a car. Now, since you have a image recognition results and reproject onto 3D laser sensor coordinates, If you can, for example, improve the quality of image processing, then you exactly know what 3D real world looks like around the cell. But again, because I'm not an expert in image processing, sometimes we miss the, detection is not always perfect, but still it is a good quality for prototyping the system. And now if you want to add pedestrian detection, then the problems are more difficult because sometimes on the image, vehicles and the pedestrians are overlapped. So sometimes distance informations are confusing. So red cube represents the vehicle, but sometimes it shows up here because they are on the image, vehicle and the pedestrians overlapped. So we have to fix it in the future. But it's again enough for providing a platform because somebody who downloaded this platform can improve the system. Okay, I wrap up almost, but now I only talk about perception of the real world. Once you perceive the scene along yourself, now you have to make a plan about what to do. This is more popular in the robotics domain, but for example, what we can do is to generate possible path considering your current pulse and current velocity, because vehicle is not a mobile robot. It cannot make a sharp turn. If you do that, then you will be crushed, right? So you have to consider dynamics of the vehicle depending on the angle of yourself plus the current velocity. Maybe for the vehicle, maybe you are restricted to 6 ways for the planning. If you try to make a 90 degrees curve, then it's not going to be feasible. So considering vehicle constraints, then maybe this is a path that you could take from now on. So for instance, projecting those possible paths on the 3D coordinates, then for example, because this scenario you don't really have obstacles on yourself, in front of yourself, so you don't have to take another path. But if you have a parking vehicle in front of yourself, then you can select other path to detour the parking vehicle and so on. But it's also difficult since it is going to be more control problems now. You can try, but you will see the vehicle may not be very stable to avoid the parking vehicle. But again, since the reason is because we are not an expert in the control. So if you collaborate with the control persons, then you can make it smooth. Okay, now so 3D map again. So let's come back to 3D map. So 3D map is a strong tool because you already know static information. For example, where is the cross zebra zone? Because by probability, pedestrians may show up on a crossroad. So it's important to detect crossroad because high probability there may be a person. Again, since you have a map and you know the location in itself, then you know when and in what distance the crossroad shows up. So this is another example. So you already know this is crossroad, but it was okay. And next crossroad is going to show up. And here, because we are extensively trying to detect something on the crossroad, because crossroad is more dangerous than other area. So this is more like traffic rule, right? So when you are driving and when you are approaching to crossroad, then you may be more careful about driving because passengers may show up.
In Japan, when there is this zebra crossings,
Mm-hmm.
I mean, do cars stop usually or?
Yes. Pedestrians are always prioritized.
Also in Portugal most of the time, but in Greece
That-
we ignore that.
That's kind of market competition, right? So which doesn't mean only a single model applies, right? So in different country, you need a different model. So you have to do machine learning or you have to do deep learning for every country scenario. So that's why makers are very focused on kind of machine learning or deep learning stuff because they want to get more markets. Well, I am working with Chinese institutes. It's more aggressive because cars may be more prioritized than so that's a country or more tradition. Okay, so well, this is basically what we are doing, and sometimes we try to use 3D map in a different way, not only for autonomous driving, but showing a virtual reality because you exactly know what the shape of the real world around yourself. So you can put some texture on 3D map to kind of imitate, it's not totally virtual because we reflect the shape of the real world. So you can, while you are driving, for example, you can say replace the castle with your building, and then when garage is gonna be open, then you can make it more fun to kill your time. So because it's autonomous driving, you don't really have to focus on driving, so you can use your time in a different way. Maybe, so gamification is one of the projects that we are interested in. So it's a significant amount of time if you can save your time when you're driving. So it's gonna be a big market, and gaming is one of maybe ideas to share drivers. So for instance, when you are stopping at the red light, you don't really have to keep looking at the red light. Just the monsters are coming down, and you can just shoot in. And also, maybe some persons are showing up. You don't really have to recognize it's a person. The event that you must know is you try to avoid something. So in that case, maybe in the real world, persons are there, but in the virtual world, you can just make a hole. So the vehicle is turning to the right because it is trying to avoid the hole. So it's kind of not augmented reality, but it's more human interaction with autonomous vehicle. It's going to be a very interesting topic in the future once the autonomous vehicle is in the market. Okay, so trying to finish. Now everything that I demonstrated today is open source. So if you download the software from our website, you can basically do the same thing as what I demonstrated. But if you want to operate a real vehicle, then you need a real vehicle. But we provide a simulator. So most of all the videos that I showed you today, we didn't take it from the real vehicle. So we provide a simulator, so you can basically create or test the function on the simulator. We can skip. So we provide this part. So it's a Linux or more real-time extension to the Linux, and this is very strong tool, which is a component-based system, because we have a lot of researchers, developers. They don't communicate very often. So somebody who is outside of the, for example, project, but still if they build their algorithm on top of the robot operating system, if it's on top of this, then we can easily integrate their algorithm to our system. So, and this is not very good interface, but it's so it's GUI tool to make operation somewhat easier. So now he's selecting the data to the simulation. So we are not on a real vehicle. We are in a laboratory, but he's selecting a data that we collected before. And now he's selecting 3D map information, which is provided the files. But again, you can also download them from cloud, but sometimes because you don't want to use say mobile or network resources. So sometimes you can just load it from local file system, and you click and launch the viewer. And this viewer is not ourselves. It is provided by ROS package, but this is very strong viewer. So now you can display 3D map information, and this is the log data that you collected way before. So you can replay what happened in that scene. So since the system is everything is integrated, now actually image is coming every 10 milliseconds, and LiDAR laser sensor data is also coming into the system every 100 milliseconds because it's replaying. Now here's a it's a localization, it's a matching algorithm. Now the vehicle is localized, so you don't have to do anything else now because the vehicle is now understand where he's driving on the map, and he's selecting more function to. But this needs instruction because if you download it first time, you don't know the algorithm at all, so you need some instruction. But he is now loading the path to be followed. And in order to create a demonstration, maybe sometimes you want to change the angle of the view. So the viewer supports to change the angle of the view because it's 3D. You can look at the vehicle from any angle you want. So, and of course, because I'm a real-time systems person, for example, the system looks like this. So it's called, in our community, it's a DAG, it's a direct acyclic graph. So you have to solve the timing problem of such systems. Each node must be finished in a certain time of period. So this is going to be a real-time systems problem. Okay, if you need a support, you can ask my company. So I launched the company in last December. So it's open source. If you are maybe students, you can spend some time to understand the software. But for industrial people, sometimes you want to save the time. So they will ask us, the company, to, for example, set up the vehicle. And we already have 16 vehicles from 5 different companies, autonomous vehicle. We only need 2 days to make it autonomous. So it's very time efficient. And we also provide a package. So if you want to try embedded systems rather than desktop or embedded system, rather than laptop, then you can also ask us. Smartphone applications we also provide. And we are now developing a vehicle, collaborating with an EV startup company in Japan, so that we can just provide a vehicle rather than a system. Okay, thank you. Maybe that's it. If you have more questions, I'm happy to answer, but I can conclude the presentation at this moment. Thank you very much.
Thanks for the very interesting presentation. So my question is, so what kind of, what were the most interesting issues that you came up when you actually went on the road, which you did not anticipate at all?
So what most interesting what?
Issues, what interesting things that the most interesting. I'm sure there are many that were.
Maybe guaranteeing the safety, say, or guaranteeing real time, right? So if somebody asks me to do a test drive on a public road, yes, if we try a drive, then we may be able to succeed. But we don't know beforehand if we can really succeed or not. Because we can guarantee, for example, 80% or 90% of safety, but there is no 100% guarantee. So now it's going to be a societal discussion if your system is not 100% safety, but still, can you allow that system to operate in a real world with real humans? So if somebody says you need 100% guarantee, then maybe we cannot guarantee it, because since we are scientists, we know that there is no 100% guarantee. So in order to make a public law testing, the way of ensuring the safety of the experiment is the most important or interesting problem. Or otherwise, we can just see the results of the experiment. Sometimes it fails, sometimes it succeeds, but in either case, you get nice data, right? But for public law testing, because it's not closed place, it's open place, we really need to guarantee the safety of the testing with the real world. That's the most interesting problem to me.
Related to the same problem about safety, related to the safety problem, so it seems that most of the system relies on that 3D map, which is downloaded at runtime. What happens if you lose a connection, you cannot download the map? Is the vehicle just stopping itself, or
Yeah,
it
technically,
can still drive somehow in the environment with the new information?
yeah, so, well, technically speaking, it's not implemented yet, but it's technically or ideally, system must be must be hierarchical. Like if autonomous driving system, depending on 3D map, may not work, then more a minimum set of the function must be activated to immediately safely stop the vehicle. For instance, you can just park to the place, the most closest place from yourself, which is allowed to be parked, something like that. So emergent system and general autonomous driving system, I believe they must be separated somehow, because you don't want to fully depend on autonomous driving system. Like we are going to be connected now, so if you lose the connection, as you said, then you may not guarantee the safety anymore in 10 seconds or 20 seconds. But since you still have a local understanding, so in 3 seconds you may be able to stop safely. So kind of hierarchical system is required.
Another question then, it seems that this kind of system is very prone to security problems.
Yes.
Because if someone is injecting wrong data in your map on the data center, the vehicle may think that he is somewhere, but it is somewhere in a completely different place.
Yes.
Or the road is not where it thinks it is.
Yes. So security.
How will you protect your system against this kind of attacks?
Right now, based on, because internet security problem has a long history in a different community. Now we definitely have to collaborate with them. Maybe as a buzzword, it's called IoT, perhaps Internet of Things. How you can ensure the security of things connected each other, which is like internet. So, but again, because embedded systems security is a different problem as well. So it's really open problem, but I believe that we don't have to create everything from scratch in security problem, because security community has a lot of ideas to ensure the security of mobile systems. So we can maybe collaborate. But again, since the car is a safety critical system, I'm not sure if 99% of secure system is sufficient for safety critical system or not. But it's open problem. I don't have an answer yet.
What is the size of the object that you can detect?
Size of what?
The object that you can detect with your sensors.
Depending on, oh, I see. If you only have a laser sensor, then depending on the distance, because laser sensor has a multi-layers. But if objects are close to you, for example, if there are 46 layers, then all of them may hit the object. So it's high resolution. But if you have your object in long distance, then maybe only 3 or 4 out of 64 lasers can hit. So if you have only 4 points on the object, you may not be able to recognize if it's a car or pedestrian. So for laser sensors, it's depending on the range of the distance. But that's why you want to fuse the different sensor, because the camera now can detect more long distance object if you train the image recognition algorithm very well. So for us, maybe 100 meters or 200 millimeters is the limit of what we can detect by camera. So if camera knows what it is, then if only a few points of the sensor data can hit, then you know it is a car and you know how long far away from yourself. So the sensor fusion allows us to detect maybe 100 meters or 200 meters range detection, but if you have only single sensor, then it's very restricted.
And why don't you use radars instead of laser sensors?
Because radar is it's not precise. Radar can reach say 200 meters or 300 meters, but it's pretty vague. But laser sensor, it's always centimeters or millimeters precision. So we are more preferable on a laser sensor.
I have it's really extraordinary what you have done in this project. And one question I have is, every year there is a lot of progress, right, in terms of autonomous driving, and I can't believe that Google is so much ahead of you. It must be incredible what they have done. Is there the same excitement in other domains rather than technology? Like, for example, in Japan, does the society is preparing itself to welcome this kind of technology in terms of laws, in terms of rights, insurance? Is it a move of the society to adopt this kind of technology, or is just engineers getting excited about it?
In Japan, everything started. So last year, most of companies which asking me to make collaboration is car companies or supplier companies or electronics companies. But after this year, because the Prime Minister stated that we have to make it realized before 2020 Olympics in Tokyo.
Okay.
So now, like insurance companies or material companies, like because you have to embed the sensors. You don't want to keep disclosing on top of the vehicle, so you have to embed inside the vehicle, but you need to change the materials because the laser sensor cannot go through the body of the car. So material companies, and of course IT service companies, because they want to make a service on top of using the autonomous vehicle. So the society has been actually changing, and we are changing the law. Now the police of the police of the Japan, not local, they actually opened up the guideline about how to make a public road testing. So now not only for us, but also for any other institutes, if they follow the guideline from the police, they are allowed to do public road testing. So now the society is apparently moving ahead. But it started this year.
So far it looks like everybody is using their own data, like 3D map, you use your own 3D map, your own deep learning network, Tesla, they have their own data. So do you think on this emerging market there will be competition between the companies who provide this data, or one of the data-rich companies like Google will dominate because they already established lots of their presence in the roads and they have provided lots of data?
So in Japan, government and car companies are working together to define the market. So for 3D map, it's going to be a share market. So for instance, car makers or rich companies can support map makers to create the common standard map, which can be used by a lot of other companies. So for instance, the map is a shared standard. They don't want to make competition on the map because they don't want to use different maps. The map must be the same. However, on top of the map, for example, a planning algorithm or deep neural net models, they're going to be competition. So each company can provide, hey, our company provides more comfortable driving model, so why don't you buy our vehicle? So it's a separate market.
So it's interesting that you're using 3D map for the location, like you said, but it's much more reliable than GPS. And what I wanted to ask is, have you tried anything indoor, like parking spaces? And in those cases, are you mapping and using the same thing as the outdoor?
Mm-hmm.
So is there a difference in what you're doing in the
The base technology is the same. We can definitely, so it's a SLAM.
Yeah.
Localization is based on a SLAM, and the SLAM is originally designed for indoor
Okay.
mobile robots. So we definitely use the same idea. However, because it's on outside, it is more open space, just more uncertain conditions. However, because the sensor is pretty rich now, so if you have a expensive sensors, then you can basically use the same idea from the indoor technology. But if you try to downsize sensor, or if you want to reduce the cost of the sensor, and if you want to switch to more cheap sensors, then it may not be the same. So, but right now we use exactly the same idea from indoor localization.
So one question about the software. You showed us how you can use the software to replay your experiments, right? And is it possible also to do like simulation? You have a model of the car that you can drive around without need of having the real car?
We don't simulate dynamics. So if you want to test control, if you want to see if the vehicle really, say, moves the steering angle as you operate it, as you send a command, which we cannot test. What we can test is before dynamics. If you say you can visualize, for example, the path of the vehicle that should be followed, which we can confirm on the visualization, but you cannot move the vehicle. If you connect the system to car simulator to actually move the car model as your command, then yes, it may be possible to
Okay. So given a point, you can from the simulator you can get, for instance, the view of the car, but you cannot move the point.
No, we can move.
Yeah, but not in the model of the car.
Yes.
Okay.
If we say, hey, move to here, then the simulator moves the car here, but it doesn't simulate steering or accident brake strokes.
I have a question about the scheduling policy that you are using. How are you handling scheduling at the moment? Because it seems that you have a lot of asynchronous events, and you are, as far as I understood, using real-time Linux underneath. So it's kind of complex to deal with all the latencies. So that's why I would like to know more about it.
So surprisingly, we use fair share scheduler because we didn't have time to tune up the scheduling policy. So we don't use EDF, we don't use fixed priority. Well, we only put high priority to localization because localization is the most important function. If you fail to localize yourself, then the steering moves like this because he doesn't know where we are. So we put high priority than other function onto the localization module. But other than that, we just let them run. But we know that it doesn't guarantee safety. So it's a next stage because we built up the platform now. So if you can share the platform with other researchers, then especially I'm interested in that.
Okay. And how many tasks do you have? I mean, there are a lot of tasks that are like fixed, and then you have a lot of events that are produced that are asynchronous.
Yes, so I think there are no static events. Okay. Almost everything is dynamic. Okay. So you have to, however, there is a dependency. So there may be not so many combinations of period because they are actually synchronizing with each other. If you decide, hey, run in 10 Hertz, at 10 Hertz, then most of the nodes are running at 10 Hertz, which is 100 milliseconds of period. So, but still we have a scheduling problem because it's a data dependency, pipelining and so on.
Because as I see it, the scheduling will have to be handled like during runtime. You need to have like a runtime scheduler. I mean,
yes, it is.
Yeah,
it's not a static scheduling.
Exactly.
We really need runtime scheduling.
Okay. Thank you.
So related to that, is this model of your system, timing model available?
No. But yes, so again, because we have this platform, now, for instance, formal verification or system security persons. They are more interested in the system. Now, they are originally interested, but they didn't have a platform to test their ideas. But now we can provide a system, so we can now collaborate, but not yet. We are going to collaborate with verification or security people.
No, I was more thinking about if you want to test new scheduling policies, for instance.
Oh, I see. That's what we can do using this simulator, because you can replay a scenario, you can run any modules, but since they are running on the Linux, if you know how to modify the Linux scheduler, then I think you can test.
And the theoretical model. So for instance here I see that okay, you have done with all the dependencies, you have an example of scheduling there, but are those data with the timing properties of each node and so on?
Oh, I see. That
available somewhere?
that's actually you can set by using GUI. So you can set, hey, for image processing, run in 30 milliseconds. It's up to you. There is no there is no formal specification of how timing parameters of each node must be. Nobody knows it, so you can
because it depends also on the platforms.
Yes, plus maybe depends on automotive company, for example, what specification is more safe than other specifications. But we don't know the specification, but at least we can specify the parameters as you like.
One last question.
Going back to the society thing, in your experiments, how much annoying it is to be in the driver's seat of an automated car? Is it at all annoying, or is it relaxing, or what's the experience, user experience?
Until last year, because nobody knew that we are doing public test, so I was not annoyed at all.
Okay.
But recently, because the government moved, then automotive companies, they also trying to do a public road testing. So now a lot of regulations showed up, and now the government knows that we are doing autonomous driving tests. Actually, there are 2 or 3 institutes who are actually doing public road testing. So we are now significantly asked to guarantee safety. So for example, before we do autonomous driving test, then we have to submit a lot of documents saying, hey, we analyze the risks of the test. For example, I don't know, there are more than 100 items to check what the risks, and each risk has what kind of how dangerous it is, and if the risk is somehow more dangerous than what the government can allow, then we have to propose the idea of how to reduce the risk. Then if all the risks are below some threshold, then now we are allowed to do a testing, which doesn't happen, which didn't happen last year, but this year, because of the government, yes. It's not annoying, it looks what it should be.
Okay.
So now we are trying to follow the guideline of the public road testing.
So thank you again.
Sure.
Okay, thank you.